So yeah, so today our discussion will really focus on Neumann boundary conditions, specifically in Poisson equation problems. We'll introduce a condition that we need in order to ensure existence that we didn't really need in the case of Dirichlet boundary conditions. If you remember from the homework that you just did, you have essentially non-uniqueness of solutions once you start to introduce Neumann boundary problems, but that also means that there's some Neumann boundary problems that you can't solve. Similar to what happens in linear algebra, where if you have a matrix that's not full rank, for instance, right, you can have infinite solutions to associated systems of linear equations, but some systems are not solvable. And this is sort of related to ideas like the Fredholm alternative, for instance, which you'll see, I think, in functional analysis. Okay, and then once we talk about this, we're gonna, the last sort of portion of the class is really focused on traveling waves and methods for sort of converting nonlinear PDEs to systems of nonlinear ODEs that we can solve using some phase plane analysis or analyze using phase plane analysis. So I want to kind of maybe wrap all that up before Thanksgiving, and then actually I think we won't have class the Monday after Thanksgiving or the Wednesday before, and then we'll just do some review problems that last week ahead of the exam 3. And exam 3 is non-cumulative. It's just going to be on Laplace's equation, Green's functions. Yeah, sometimes I put a nonlinear wave equation on there or not. But yeah, it'll be sort of the last half of the semester stuff. Okay, all right. So today let's talk about Neumann boundary conditions. Okay, in essentially the Poisson equation. Okay. So let's consider the following just general description of the Poisson equation. And let's just define it just to have something concrete to show, and so that I can talk about some of these differences between Neumann and Dirichlet. I'll put us on the half plane, okay? And so our boundary condition, because this is going to be a Neumann problem, just make that 0. And the boundary is just going to be x. The x lives in R2, right? Such that x1 equals 0. Okay. All right. So let me just remark, if this were a Dirichlet problem, okay, essentially the way that we should find the solution, okay, is to use an odd reflection principle of the free boundary problem. Okay, so remember that in the case of the heat equation, the way to sort of zero out the boundary is to subtract off the fundamental solution reflected to the other side, of the real space where you are not solving the PE. Okay. In the case of Neumann boundary condition, we want to use even reflection. Okay. And so recall the heat equation here, okay? So let's see how that works in this case, okay? Well, to get the Green's function, which I can then integrate against my inhomogeneities, okay? I would want to solve the problem Laplacian of G is equal to delta of x minus y, right? And then dg dn is equal to 0, essentially on just on the boundary here, okay? The even reflection of the fundamental solution in this case is going to be what? Well, it's going to be g of xy is equal to phi of x minus y plus phi of something I'll call x hat minus y, okay? Where x hat, I really don't like where I've written this. I'm gonna rewrite this. Tablet's just not always enough space. Okay, all right. So x hat here is equal to minus x1, x2, okay? And so essentially, it's just like the method of images, right? But instead of subtracting things off like we would need to in the case of Dirichlet, we're adding them together, okay? And so does this work? Let's check, right? Does this satisfy, in particular, this boundary condition, okay? We know that it should satisfy this here, right? Because we're placing the term that we're adding outside of the domain that we're worried about, right? So for all of the values of y, right, inside of omega, we're never going to run into a singularity, okay? We want to make sure we put that singularity outside. So now dg dnx here, okay, is going to be the normal derivative of the first term plus the normal derivative of the second term, right? I'm just denoting that I'm differentiating with respect to x, not with respect to y, okay? But I'm only worried about this satisfying the boundary condition on the boundary, right? So so I only need to check this on the boundary. So let's look at our boundary here, right? What is the normal on the boundary? Okay, so here's my d omega, right? It's always just a vector pointing straight down, right? So, excuse me, I mixed things up. Sorry about that. It's always a vector pointing left. Okay. Here. And this vector is just minus 1, 0. Okay. So this is our normal vector, okay, on the boundary there, okay? And then to compute our normal derivative, we just take our gradient and then we dot it with our normal vector, okay? So d phi dnx is equal to minus 1, 0, dotted with the gradient of phi x minus y, okay? D and d of phi with the argument x hat in there, okay, is going to be equal to minus 1, 0, dotted with the gradient of phi x hat minus y, okay? where essentially dx1, right, of phi of minus x1, x2, y1, y2 here, right? So here's our x hat, okay, is going to be equal to minus d phi dx1 minus x1, x2 minus y1, y2, okay, applying the chain rule here, right? And this gradient will be straightforward. It'll just be d phi dx1, right, without the minus sign out front. So the minus sign essentially pops out from the reflection, the image point essentially that we've taken, okay? And when x1 is equal to 0, okay, remember we just have that x is equal to just this x hat, okay? So that means that or dg dnx then, in this case, is just going to be d phi dx1, right, evaluated at 0x2 minus y1, y2 minus d phi d x1. So I think that, yeah, I should switch the signs here, right, because we're taking the dot products here. 0x2 minus y1, y2 equals 0. Okay, which is what we need. Okay. All right. So so we have a way of constructing the Green's function. Okay, but I still haven't really told you how to create a solution yet. So we'll talk about that next. Are there questions about this sort of even reflection principle here? And you can extend the idea to the unit ball, for instance, but it's it's just a little more complicated, right? But the idea still is that you'll take an image point and you'll sum your boundary correction term in that case, right? Because essentially you'll have a flip of a sign, right? Once you flip about the particular depending on the side of the ball boundary that you're on. Okay. All right. So let's talk now about solutions, right? So we've talked about just constructing the Green's function. Let me go more general, right, to solving PDEs with Neumann